Okay, so let's begin. So this week we have a nice presentation by Trung, who's going to talk about Bayesian neural networks. So please go ahead.
So hello everyone, my name is Trung, and today I will present my paper tackling covariate shift with node-based Bayesian neural network. Our work is selected for oral presentation at ICML this year, and this is a joint work with Marcus, Luigi, and Sami. First, I will discuss some background knowledge. So we know that generalization is a core problem in machine learning, and currently neural network perform very well when the test data is similar to the training data. But when we give it an input that comes from a different data distribution, then it will return a very random vector that unpredictable. We cannot predict its behavior on this new data. So this is our distribution test data. And this is a problem called covariate shift. And in our paper, we focus mainly on covariate shift due to input corruption. So on the left-hand side, I got an image of a frog from the Cypher10 dataset. And on the right-hand side, I got that same image, but under different input corruption. So currently, neural network will, in a classification task, a neural network will return a quite accurate prediction on clean image. But when we start to corrupt the image more and more with more severity, then it output will degrade rapidly, and eventually it could return like a different class. The desirable behavior in this case is for the output vector to converge slowly toward the uniform probability vector. That is a nice behavior in this case. And so for the covariate shift problem, the usual go-to method is Bayesian method. So we expect, so in a Bayesian neural network, we learn a posterior distribution of the weight given the training data, instead of just learning a point estimate like the standard deterministic neural network. And so we expect Bayesian neural network to perform better than the deterministic neural network under covariate shift, because they combine like prediction from multiple samples from the posterior distribution. However, a recent study showed that BNN actually perform worse than the MAP model under corruptions. This is because in Bayesian neural network, we usually use the Gaussian prior as the weight prior, and this prior does not have a good inductive bias to handle input corruptions. And recently, there's a alternative to Bayesian neural network called node-based Bayesian neural network. And so above, you can see the node BNN, which is we introduce stochasticity in the output of this model by multiplying each node in the neural network with a latent random variable, instead of like inducing stochasticity over the output by considering the weight and biases as the random variable. Here we consider weight and biases as a fixed parameter, but we introduce some latent random parameter into the model. An example here, we have MC dropout, which we use Bernoulli random variables, or rank 1 BNNs, which we use a mixture of Gaussian random variable. So this previous paper introducing rank 1 BNN showed that this type of node BNN actually perform quite well, better than the MAP model under corruption. So here the red line show that this model achieved higher accuracy under more increasingly more corrupted input compared to the MAP model. And so here I will describe formally the node BNN model. So this model only different from the standard neural network in that we multiply the input of each layer with some latent node variable before feeding it into the layer. And in this presentation, I will use this symbol to denote all the collection of all the random variable in the model, and this symbol for the latent distribution. For a sample from the latent distribution, I will use this notation to denote the output of the neural network under one sample from the latent distribution. So in this node BNN model, there are two types of parameters. The first one are the weights and biases, which we find the MAP estimate. The second one are the latent node variables, which we infer is posterior distribution. And so the original motivation of this model is that it is more efficient than the weight-based BNN, because if we look at this table here, the number of weight is much higher than the number of nodes in a typical neural network. So we decrease substantially the size of the posterior to be inferred, which simplify our inference problem. So the goal of our paper is that we first provide some insight into the robustness of node BNN under input corruption. And from this insight, we propose a method to further improve this robustness. So why do nodes BNN generalize well under corruptions? Our intuition is that the distribution of the latent variable induce a distribution of implicit corruption in the input space. So what we mean is that, let's say we here have a node BNN with its own latent distribution P of Z. If we give it an input, then we will have a distribution over the output. Now, instead of having a latent variable at every node in the model, let's say we have an input distribution. We hypothesize that there exists a distribution of corrupted input in the input space, such that when we feed the sample of this distribution into this deterministic network below, we will obtain the same distribution over the output. So let's say we have a sample from the latent distribution, which gives us a sample from the output distribution. There exists like a corrupted version of the input image, such that when we feed this corrupted version through the deterministic model, we will obtain a similar output vector. So now we introduce like a method to visualize this corruption. So first, we hypothesize that a corrupted version of the input is a sum of the original input plus some corruption mask we denote M. And so given a sample from the latent distribution, we can approximate the corresponding corruption mask by minimizing the following loss function using gradient descent, where the first summand just match the output of the node BNN under that sample from the latent distribution and the output of the deterministic model under the corruption mask. And then the second summand just regularize the norm of the mask. And here I give an example of 3 corruption masks under different regularization strength. So here we can see that when lambda increase, the severity of the corruption decrease. And also here we can see that there's some meaning to this corruption mask, because we can see like a resemblance of a horse in the corruption mask. So from this intuition that the latent distribution induces like a distribution of corruption in the input space, we hypothesize that by increasing the entropy of the latent variables, we will also increase the diversity of the implicit corruptions. And thus, by training under more diverse corruption, not BNN become more robust against the natural real-world corruptions. So to test this theory, we have this simple small experiment where we obtain two node BNN model with the same architecture. One model has a low latent entropy and the other has a higher latent entropy. And we have trained both model on the Cipher-10 dataset, and we test it on the Cipher-10 corrupted dataset. And so in this small experiment, it does shows that the high entropy model achieve better performance in terms of negative log likelihood compared to the low entropy model under different corruption intensity. And we also ask ourselves that is each model actually robust against its own corruption, because we have presented before a method that can visualize the corruption mass from the latent distribution. So to answer that question, we use each model to generate a set of corrupted test images and then evaluate each model on its own generated corruptions. So in this small experiment, the answer is yes, because we can see that the performance under corruption is only slightly worse than the performance on clean images. So the degradation is not much, and we conclude that yes, each model here is thus robust against its own corruption. We also test each model on the corruption generated by the other model. And here we can see that the low entropy model is less robust to the corruption generated by the high entropy model than vice versa. So this further support that higher latent entropy model is better for corruption. So how do we increase the latent entropy? First, we will discuss a method to train a node BNN model. So as stated before, there are two types of parameters in this model. The first one are the weights and biases, which we find MAP estimate. And the second one are the latent node variable, which we infer its posterior distribution. And in our paper, we use variational inference as the training method. We approximate the complex joy distribution of the latent variable Z and the weight and biases theta using a simpler parametric distribution Q by finding the parameter of Q that minimize the forward KL diversion between Q and P using a gradient method. And here in our paper, we choose the variational posterior for theta as a Dirac delta measure to find the MAP estimate. And here we denote theta hat at the MAP estimation of theta. And the variational posterior of Z, we chose the mixture of Gaussians. So the training objective is we find theta hat and phi maximizing the following the evident lower bounds, where the first term is called the expected log likelihood. It will fit the variational parameter to the training data, while the second and third term will regularize the variational posterior of Z and the MAB estimate of theta respectively. And so now to increase the latent entropy, we will introduce the gamma entropy term to the original elbow. And this gamma entropy term will increase the latent entropy when gamma is larger than 0. And we call this new objective the gamma elbow. So it turns out that maximizing the gamma elbow is equivalent to minimizing the KL diversion between the variational posterior and a temper true posterior, where the temperature tau is equal to gamma plus 1. And here I have some visualization on the effect of gamma on the target posterior. So here we can see that as gamma increase, the mass of the target posterior become less concentrated, so it's spread out more. And when gamma is larger than 0, it also mean that the temperature tau is larger than 1. And in this case, we call this hot posterior. And interestingly, hot posterior are used in Bayesian statistics to alleviate the problem of model misspecification. And here covariate shift can be considered as a model misspecification because we use a model trained on under different assumption about statistics of the data. Here we present some ablation study. So first I will show the effect of gamma on corruption robustness. So in this experiment, I use the VGG16 architecture and the Cypher 100 dataset. And for the variational posterior of the latent distribution, I use 1, 2, and 4 Gaussian component. And for brevity, I divide gamma by k in the x-axis. So here we can see that under different corruption intensity and mixture posterior, the performance improve as gamma increase up to a certain optimal gamma value. And then after that, it degrades. And here I plot the optimal gamma value for different corruption severity level. So here we can see that higher severity require higher optimal gamma. So we can conclude that gamma controls a trade-off between the in-distribution and out-of-distribution performance. And here we also suspect that our method provide improved learning under noisy label. Since previous studies have shown that it is harder to memorize random label than learning generalizable pattern, we theorize that if we corrupted a training sample with wrong label with sufficiently diverse corruption, then the model will fail to learn the wrong label, to memorize the wrong label. So to test this theory, we will train a ResNet 18 on a Cypher 10 dataset, where we take 40% of the training sample and we just flip the label of that training sample. And so on the left plot, we show the average negative log likelihood of the training sample with correct label in blue and incorrect label in orange under different gamma value. And here we can see that as gamma increase, the trending negative log likelihood of the wrongly labeled samples increase much faster than the negative log likelihood of the correctly labeled sample, indicating that at high gamma value, the model failed to learn the training sample with wrong label. And in the right plot, we can see that because of the phenomenon we see on the left plot, the training negative log likelihood is also achieve the best performance under a high gamma value, like close to 80 here. And finally, we present some benchmark result. So here we compare against two wave-based BNNs baseline. The first one is SWAT, and the second one is a cyclical stochastic gradient Hamiltonian Monte Carlo. And here we can see that under the ResNet 18 and Sapphire 100 setting, the node BNN in blue perform better than the baseline BNN under corruption across different metrics, and it's only worse than the baseline on expected calibration error on in distribution data and on low-level corruption. And a similar result is observed for the pre-arc ResNet 18 and the tiny ImageNet setting, where the node BNN also produce the best result under corruption. So in conclusion, we have shown that the latent variable simulated a set of implicit corruption, and by training under this corruption, node BNNs become robust against natural corruption. By maximizing the entropy of the latent variable, we increase the diversity of the implicit corruption and thus improve the robustness of node BNN. We demonstrated that the latent entropy controls the trade-off between in-distribution and out-distribution performance, which more severe corruption require higher optimal latent entropy, which decrease the in-distribution performance. And finally, we also show that our method provides robustness against noisy training label. And more information about the paper can be found as this URL below with the code and the paper. That's the end of my presentation. Thank you for listening.
Okay, thanks a lot, Trung. So any questions either from here or from Kumpula? Okay, so I guess then I have a question. So what's the next step? Are you going to continue this line of work or any thoughts?
So I think one of the possible steps is to find a better indicator of robustness than entropy. So here entropy, we found that entropy is one of the simple way to increase the robustness, but there are probably a different metric that incorporate more the shape of the posterior distribution that can be more correlated to corruption robustness. And also another direction is to actually represent the latent posterior with a specific corruption, so rotation or the transformation, because here the multiplicative effect of the latent variable it seems to correspond to this short noise where we take a pixel and we randomly increase or decrease its value. And yeah, by doing that, we somehow also achieve corruption on also in robustness in different type of corruption. But it would be nice to also zoom in and have a latent distribution that target different type of corruption. Yeah,
very good answer. And I guess as a follow-up, I wonder if you could if you could maximize the entropy in the input space or in the output space, because right now you maximize just the entropy in the latent parameter space, but you can also just transform this distribution in the input space or to the softmax space and then maximize the entropy in either of these two spaces. So I wonder, like, in which space which of those distributions should we make maximally diverse? I wonder if you have any comments on this.
So I think that for the distribution in the input space, we can make it maximally diverse. But for the output space, it's a little bit tricky here because we don't want the output space to be too diverse on the sample inside the training data set, because then it would lead to the problem of underfitting, I think, because for the training sample we already know it's correct label, so it's really hard to make the output vector diverse there. But we could make the output space diverse on sample under corruption or some on out distribution sample. Yeah.
Okay.
This is not exactly my field of study, so I probably didn't get a perfect of the whole thing, but I was just wondering, what is the difference between this approach and just adding Gaussian noise in different layers? Like you want to make the neural net more robust and adding more noise makes usually sometimes the network more robust. So what is the difference, especially knowing that high entropy is latent there? What is the difference between this and just adding Gaussian or some other?
Yeah, so what?
Can you summarize the question?
So the question is, what is the difference between this approach and just adding Gaussian noise to each layer during training? That's what you mean? Yeah, so I also wonder that question, and what I find is that, so here we learn the posterior distribution of the latent variable, so we fit the specific noise into the training data, and that will prevent the problem of underfitting. Yeah, so when you add, and also the second thing is that multiplicative noise is more flexible than Gaussian noise, because the multiplicative noise is corresponding to Gaussian noise, but depend on the data also. Like it's not a fixed noise, but that noise also depend on the feature of the data. Do you see? So it is more flexible and it's avoid the underfitting problem. Yeah. So I already found some paper in the adversarial defense field where they add Gaussian noise in the input space, so to make the model more robust against adversarial sample. So that is one of the approach that you mentioned. But here our focus is different, like it's input corruption, and I find that this approach is better.